Good morning, ladies and gentlemen, or I guess afternoon. Hope you guys are all doing well. Please forgive the heavy overexposure of the camera. It's kind of bright in here for some reason at the moment. So today, what we're going to do is we are going to be working on the conservation of linear momentum. So this is a super cool topic. I love it. It's super important. I guarantee you guys are going to have a question like this on your diploma, on your unit test, and on your assignment. So you need to know this. All right, lesson settle in. Okie dokie. So, ladies and gentlemen, I'm going to take this opportunity to talk about a piece of your data sheet. And at the very back of your data sheet, I want you guys to find this section. So you're going to come to the back that looks like this. And you're going to come and find this piece. Okay, where it says physics principles. I'm pretty sure it's backwards in what you guys are seeing, but you get the idea. This is a section that is going to come into play in your diploma exams in the numerical response area. So it's a theory question where you will see a bunch of data and a calculation that you have to do, and then you'll have this numerical response question, which is, which physics principles are used in this scenario? And with that, they mean these principles here. Okay, we are going to go through each of these one by one as they come up in the course, and I will point them out to you. All right, which brings us to the very first one that we are going to be talking about. So, ladies and gentlemen, you will see law of conservation of momentum. You can find this as principle number 4 on that list. Okay? All right. So, ladies and gentlemen, in an isolated system, the total momentum of all objects, so the system that we're discussing, before an interaction is equal to the total momentum of all objects or the system after the interaction. So this is essentially the idea of a collision. So this is often what you're going to be seeing. So two objects are going to come and collide. They're either going to hit and stick together, they're going to hit and bounce off of each other, so a rebound, or you're going to have one object that's going to burst apart into multiple, so an explosion. Linear momentum means it's all going to be on one plane. Okay, we're dealing with one dimension, forward and back, or I guess forward and back. Anyway, so guess what we're doing afterwards, though? Two-dimensional linear conservation of momentum. So we'll get to that later. And ladies and gentlemen, so this here is going to be our big thing. You could even rewrite this. So the P total, I often like to write it as sum of P initial is equal to the sum of P final. So remember that the Greek letter sigma is equal to, or it means sum of. So I tend to use our lovely little sigma as opposed to P total before, okay, which we actually have written there. So remember how we talked about prime, how the sum of P is going to equal to the sum of P prime. Remember, P prime is after or modified. So this would be initial, okay, and that would be final. Alrighty, all? Okay. So, ladies and gentlemen, that is not on your data sheet. You're just going to have to memorize that. Okay? So, memorize. You need to know that for your diploma. Another thing that you need to know is you need to know the definition of an isolated system. Now, an isolated system is defined when there's no net external forces acting on the system. So this would mean essentially no friction, no air resistance, nothing else. Okay? Now, this is super important because in grade 12 physics, we tend to assume that a lot of the systems we're dealing with are isolated systems. Is that the reality? No, it isn't. It is not the reality. In reality, like, we're dealing with an open system where we got matter and external forces and energy all being exchanged. So but in order to understand how something would work with friction, we need to understand the basic concept of how something would work without all of these forces acting on it all at once. So that's where we are. Okay? All right. So just keep in mind, we're dealing with no friction just so we can understand this concept. All right? Putting all this stuff together, that'll be for your post-secondary physics. All right. So the conservation of momentum will be used in a couple of different situations. What we're going to be dealing with is collisions or explosions. So your three general categories are, for your collisions, there's hit and stick, where you have two objects, they collide and they stick together. Okay, like a car accident, two vehicles can slide off after they stick together. You can have a rebound. Okay, two objects hit, bounce off. Or you can have an explosion. Now, that doesn't always necessarily mean like the fun explosions, guys. It can mean something as simple as two objects are stuck together and then they're separated. So, sorry guys, it's not always something as cool as tannerite. All right. Okay. So, ladies and gentlemen, for those who don't know, tannerite is a legal dynamic target that when you shoot it with a high-powered rifle, it goes boom. So, yeah, very fun target practice. Okay. So, what we're going to do, we have 4 steps. Okay. So, very, very important. You need to know these 4 steps. Once I can get that. Yeah. Can't get that bar to move. Okay, so we've got these 4 important steps. I'm just going to have to memorize how to do them. All right. So, ladies and gentlemen, step number 1, you can draw vector diagrams. I know it seems like a lot of work, but trust me, it's going to make your life infinitely easier for you to actually determine what the heck is going on. If you don't draw your vector diagrams for whatever reason, you're going to have a really hard time with these questions, okay? Now, if I can draw this, you can draw this. Like, I'm talking about drawing a car as a box, all right? And then, once you have drawn the objects before and after the collision and you figured out what's going on, you are going to determine the momentum of each object where it's possible. This might include some variables that our information is going to be missing. You are going to use P equals mv. And once again, watch your directions. These are vectors. It's going to make a difference. Make sure you figure out your positive and negative vectors before you start. Then, add up the momentum of all objects before the collision or explosion and set it equal to the sum of the momentum of all objects after. Okay? That is what our law of conservation of momentum is. And then you solve for what you need to do. So algebra is going to be your friend. We're definitely pulling up a whole bunch of awesome algebra. And I am going to put a huge star beside that's not a star. I'm going to put a huge star beside this chunk. I'm even going to switch colors. We're going to go like green. And I'm going to write on test less than subtle hint. Okay. Whenever I say less than subtle hint, something's on the test, and it's kind of important, guys. Less than subtle hint. This is going to be for your theory questions. Like, put a sticky on this. You are going to see questions like this on your assignment. You're going to see questions about this on your unit test. You're going to see questions about this on your diploma. This is where you come for linear momentum theory questions. This piece, like, put a sticky on it and label it so it's sticking out of your notes so you can see it. All right? That's how serious I am with this. So remember Newton's third law. When you have two objects that are going to come and collide and then separate from each other, or collide and stick, we're going to have Newton's third law. For every action, there's an equal and opposite reaction. So if you are going to take a ball and whack it with your hand, you are going to be applying a force to the ball this way. Well, the ball is going to be applying a force of equal magnitude but opposite direction that way. That's why when I hit the ball with my hand, you can feel the force of the ball hitting your hand. So what that means, during a collision between a large truck and a small car, both vehicles will experience the same force during the collision. Okay? Now that's important. So what evidence can we see of this? Well, if you have two vehicles that are going to be traveling on the highway at the same speed and they collide, one vehicle is going to be, if it's a big vehicle and a small vehicle, the big vehicle will often take less damage than the small one, because the big vehicle and the small vehicle are going to be experiencing the same amount of force because of this law. However, the small vehicle is going to be less equipped to handle that same size of force. Okay? Lesson subtle hint, this is where you're going to find your theory questions for this. Okay? All right. So we're going to jump right into our calculations now that you have a very important concept for your theory. So make sure you have highlighted that. All right, so we are going to go through 3 calculations, one of each of the categories: hit and stick, rebound, and explosion. Okay, those are going to be the 3 categories. All right, I'm going to label each one as we go. So our very first one, a 250-gram toy car traveling east at 4.5 meters per second collides head-on with a 300-gram toy truck traveling west at 5 meters per second. After the collision, the 250-gram toy car is traveling west at 2 meters per second. What is the velocity of the 300-gram toy truck after the collision? Well, when you look at those numbers, that's a mess. So much stuff going on. It's a disaster. Let's organize it. We're going to draw our vector diagrams, and we're going to list out what we have with our vector diagrams. It's going to be so much easier. Trust me on this one, guys. Okay, so this is how you're going to label things. If you do not draw your diagrams and label things out properly, you are going to have a significantly harder time than you would if you take your time and draw them. Okay, draw these. I'm going to label this object 1, and this is going to be my car. Okay, and because this guy is going to be going to the east. Okay, the mass of this car, 250 grams. I'm just going to convert that to kilograms right off the bat. Okay, then I am going to, but hold on a second. We're going to pause for a moment, guys. We're going to talk about units here. I chose to convert to kilograms because converting to kilograms from grams is just super easy, and I like kilograms. You're going to get some of the same answer in the end. But you know what we're going to do? We're going to talk about units here. I'm going to erase this, and I am going to put this back into grams. I am going to do all my math in grams. Okay? I'm just going to adjust my units. Okay? Now, why can I do this? Why am I allowed, in this case, where one side is going to equal the other, am I allowed to keep my units? Because they cancel. Okay? So, when I'm going to look, I'm going to erase this bit after, so don't write this in this spot. When I am equating one side to the other like this, I am going to have, if all my units are the same, if I leave this in grams, well, it would, instead of kilograms meters per second, it would be grams meters per second. And then that would equal grams meters per second. And well, guess what? The units cancel. So you don't have to convert units here unless they're not the same. If all the units are the same, keep track of the units so you know what you're dealing with. But you don't have to convert them unless you have ones that are different, okay? It's going to be a lot easier. All right, so we're going to stick with that, and we'll show you how it works as we go, all right? Okay. So 250 grams is going 4.5 meters per second east. Now, east, ladies and gentlemen, that's standard to be positive. We've got east and west going on, so we'll stick with that. I'm going to make this positive. Well, guess what, guys? M and V. I can just calculate my P right now. My P of object 1. Now, you have to label these guys, as we're going to have like P1, P2, P1 prime, and P2 prime. We're having 4 P's here. So label them as to what they are, because if you just say P, which P are you talking about? I don't know, right? Because you have to help me help you get the most marks possible. That means label your stuff so I know what you are trying to tell me. Okay, I may know the answer, but that's not relevant because I need to know if you know it. All right, I've already passed this course years ago. Heavens, over 15 years ago now. I'm getting old. All right. So, ladies and gentlemen, so we've got P1. I'm going to multiply these two together. Okay? So P1 is equal, in all honesty, at this point, you don't even have... I'm going to forgive you guys if you just write, because we know that P equals MV. I am fairly certain that you guys can multiply those two numbers together without writing out every single step of the way. I'm going to do that too. I am just going to write out that P1 is 1,125, so 1,125 grams meters per second. Okay, so it's still momentum, but instead of kilogram meters per second, it's grams meters per second. Just track your units and you're fine. Okay, I'm going to erase this bit here. As I'd mentioned earlier, I would. Hey guys, sorry, we got cut off. Give me a second here to just rewrite out what we already had. So we had before, we had object 1, we had M1 of 250 grams, we had V1 of 4.5 meters per second positive because it's east. We had P1 of 1,125 gram meter per second. All right. Now we're going to have object 2. I'm going to make object 2 a rectangle. Okay. So object 2 is this 300 gram toy truck. All right. Okay. So V2, this is where we're going to need to be thinking more about our direction as well. West, 5 meters per second. West is standard to be negative, so negative 5 meters per second. Okay, well, P2, M times V is your momentum. So P2, notice how we labeled these things, all right? Label them because we're going to be dealing with 4 P's in this equation. Is going to be our, by the time you multiply them together. Okay, so negative 1,500 grams meter per second. Okay, so the units are important. Okay, watch them. Okay, so now I'm going to draw a vertical line here to separate these, and I am going to write after. So this is going to be after the vehicles have collided. So I've dropped my arrow on my vector diagram. So when we come and see what the scenario is after the collision, have these things stuck together or have they come apart? Well, so as it appears, after the collision, the 250 gram toy car is traveling west. So these guys have bounced off of each other. So M2, M1. So the mass of vehicle 1 hasn't changed. It's still 250 grams. So you don't have to put like M1 prime because it's not changing. And V1 prime. Note that prime now. We've changed. Okay, the velocity's changed. West 2 meters per second. This is now negative 2 meters per second because we're going west. Watch your vector directions. Then P1 prime. Okay, you can multiply MV. You guys know that. I will be totally okay when it comes to showing your work. If you show it like this and you don't write the P equals MV and then put the numbers in and then show it, like you can do this with a 3-letter equation now. Okay, at this point, this is how I want you to show your work. Okay, so if I take a shortcut when it comes to showing the work on the screen or in class, you can take that shortcut too. If I don't take a shortcut, or I don't say don't take a shortcut, don't take the shortcut. Okay, all right. So P1 prime, multiply those together, you're going to get negative 500 gram meters per second. Okay, we are now going to draw these bucks like that. M2, 300 grams. That hasn't changed. Now we have V2 prime. Okay, so the velocity of that second object has changed. What is the velocity of the 300 gram toy truck after the collision? Okay, we don't know that. That's what we're trying to find. And P2 prime, we don't have. We can't do anything with that. Okay, so while we have done step 1, I know it's tedious, guys, but by doing this work up front, look how neat and tidy and organized that is. That's awesome. So that allows us to now go and figure out things and do the math without getting our numbers all jumbled. We've got our positives, we got our negatives. It's beautiful. It's gorgeous. Okay, organize your stuff. All right. So now I am going to come here and I am going to equate the sum of my momentum before is going to equal the sum. Now let's just do this. Is going to equal the sum of my momentum after. Okay. Now we can start putting in our numbers. Okay. Well, look, I have already calculated these two momenta here. So let's put them in. The sum of my momentum before. Okay. Now I'm going to leave the units in here, guys, to show you how these units work out as we go along. All right. Okay. Plus, I'm going to put a bracket around that. Keep that negative tidy. Okay. The sum of those guys is going to equal the sum of momentum after. Well, I have this negative 500 here. Okay. Plus my P2 prime. So that is what we have here. Okay. So we're trying to find the velocity afterwards. So we've got a couple of different ways we can go about it. I'm going to start this by solving for my P2 prime, and then afterwards I will do the P equals mv. But if you want, you're welcome to just integrate it into your equation and then do it all in one piece. Okay? Either way is fine. So let's start by solving out what we have. So I'm going to add these two guys together. I'm going to get negative 375 grams per grams meter per second, excuse me. And that is going to equal negative 500 grams meter per second plus P2 prime. Okay. Well, I can simply rearrange this by adding 500 over here. So I add 500 on the right, add 500 on the left, easy peasy. And you are going to get, with your positive 125 gram meter per second, is going to equal the value of that. Is not even close to a P. P2 prime. All right. Okay. So, ladies and gentlemen, we have our P2 prime. However, remember, P is equal to mv. So we need to find V2. That's what our goal is. So 125 grams meter per second is going to equal m2 V2 prime. I am going to divide out my m2, which is 300 grams. Okay, which gives me V2 prime. I'm going to divide out the mass, which is 300 grams. I'm going to scroll down here. And now my phone is ringing. All right. I'm going to pause this and I will be right back. Okay, guys? All right. Sorry about that. So, ladies and gentlemen, once you plonk these numbers into your lovely calculators, you are going to get your 0.416 repeating. It's going to be a positive number. Now, I'm going to take a moment here to stop, pause, and look at the units. Now, look at these units. Grams, meters per second squared, divided by grams. Those grams cancel, and you're left with meters per second. That is why when you're doing the conservation of linear momentum, you don't need to worry about converting your units from grams to kilograms or kilometers an hour to meters per second for that matter. So the units you get out are going to be the units that you put in, and they have to be consistent. So keep that in mind while you're doing these calculations. Okay, guys? All right. I mean, you can convert all the units if you want to. You're going to get the same results in the end, but just save yourself a step if you want to do that. Okay. So now, as always, sig digs, units, direction, all those good things. So when you go back and you look it up the question, we have two sig digs on that 5.0. And so we need to round these sixes. I'm going to round that up to a 2. So 0.42 meters per second. Okay, that's our units there. And now we need a direction. What did we equate our positive direction to? East. So you are going to write out the word east. You are please going to box your final answer. So I know what you want me to mark as your final answer. Okay? All right. This, ladies and gentlemen, is a classic rebound question. Okay? So you guys can go and label this as a rebound. So anytime that you have a rebound question, that is going to be the strategy in which you're going to go through. Cool? Cool. Label that as a rebound. The next question that we are going to do is going to be one about a satellite. It's fun. So, ladies and gentlemen, let us begin. Let's get ourselves organized. Start reading our question, figure out what we need. We're going to draw our vector diagrams, solve for momentum, and equate momentum before and momentum after. Okay. A satellite starts to drift off course. The path of the satellite is corrected by engine thrusters expelling some gas. The expulsion of 65 kilograms of gas increases the speed of the satellite by 7.5 meters per second. Now, once again, speed, scalar. Okay. If the average exit speed of the gas is 18 meters per second, what is the mass of the satellite? Okay. So in this case, we are going to not be worrying about the direction or we should say the east-west version of the direction of the satellite. We're still going positive, negative, but not necessarily east-west here. Okay. This, ladies and gentlemen, keyword expulsion, expelling. This is your explosion. I think I'm going to put an extra I. I'll make that part of the S. Explosion. Example question. When you have an explosion, it doesn't have to be something cool like a firecracker. It can just be like this. You have the gas and the satellite are together, and the satellite's going to throw out some of the gas, and then which will, of course, Newton's third law, is going to change the direction of that satellite. Okay? All right. So beforehand, you have the satellite, which is the rectangle. That's mass 1. Okay? Inside that satellite, you have the gas in a gas chamber, and you have satellite 2. Okay? An object 2. Well, we are going to have what I am going to call M1, okay, plus 2. So that's the mass of everything. Okay? Well, we don't know what M1 is. We don't know the mass of the satellite. That's what we're trying to calculate. So it's M1 plus 65. Okay, 65 kilograms. That's the best we can do here. Well, this is the key piece here. This is, I'm going to write this in blue to emphasize how significant this part is, because this is what is unique to your explosion scenarios. In an explosion scenario, your V1, heck, I'm going to call this V1 plus 2, because we have both objects are together. We are going to assume 0 here. Okay, now because we're talking relative here, with the gas and the satellite relative to each other is going to be 0. Okay, in an explosion scenario, you are going to be assuming, unless told otherwise, which you're not going to be, is going to be assumed to be 0 meters per second. Okay, that is the big part about your explosion questions. So what that tells us is our P1, we can even call it like P1 plus 2, is going to equal 0, kilogram meters per second. Well, that's handy. We've got a 0. That's going to make our lives easier to deal with here. Okay. Now let's look at after. Okay. Well, after the satellite is going to release gas into the void of space, well, it's going to go that way. The gas is going to go the other way. So, ladies and gentlemen, this is exactly how rocketry works. So imagine as a rocket sitting on its launch platform, and then as it shoots a bunch of burning fuel and burning hot gases out the bottom, the rocket goes upwards. And initially there is 0 momentum. So the momentum of that gas is going to be going one way. And the momentum of the rocket, or in this case satellite, is going to go the other way. But when you add the two together, it's still going to get 0, because one's going to be positive and one's going to be negative, and they're going to cancel. Okay? Isn't that awesome? I love it. So, M1, I'm going to call it M1 prime because, well, let's call it M1. Because really the mass of 1 isn't changed because we've got M1 and plus M2 over here. So M1, well, that's what we're trying to find out, ladies and gentlemen. We don't know. V2 prime. All right. Increases the speed of the satellite by 7.5 meters per second. Okay. Well, should be P1 prime is going to equal, well, we don't know the value of M1, but we know it's going to be 7.5 M1. Okay. It's the best we can do. Now, but we're going to calculate later. That's okay. M2, we've expelled 65 kilograms of gas. Okay, that's good. And if the average exit speed of the gas is 118 meters per second. Okay, this, ladies and gentlemen, is where we're going to watch our positives and negatives. To make my life easier, I'm going to actively choose to make, labeled that wrong. That should be a V1. I beg pardon. Okay, I'm going to choose to make V1 prime positive because that's my mission in the end, is to calculate the mass of that. So if I make it negative, I'm going to have like negative numbers on the wrong side of the equation. It's going to be a pain in the butt. So you can deal with it. Just multiply each side by -1, but it's this other step I got to deal with. I don't want to do that. I'm going to make that one positive, and I'm going to actively choose to make this guy negative. Okay, negative 118 meters per second. But you say, it is scalar because you said speed. Well, it's true. I did not give an actual direction. But it is going to matter because, well, they're going in opposite directions from each other. So they're vector in reference to each other, essentially, even though they have no actual given direction. That makes sense? You still got to make one negative, guys. Well, I can calculate that's my V2 prime. I can absolutely calculate P2 prime over here. I'm going to multiply those two values together, and I'm going to get negative 7,670 kilogram meters per second. Cool beans? Cool beans. Well, the same as we've done before, you are going to set up the sum of initial momentum is going to equal the sum of final momentum. Well, the momentum before is 0. Okay, easy peasy for that side. Once we go from there, we're now going to set up what it is we have on this side. Well, I have 7.5 M1. That's as close as I can get to P1, plus my negative 7,670. Okay. Well, what I am going to do is I'm going to add this guy over to the other side. So plus 7,670 on one side. 7.5 M1 is going to equal to positive 7,670 because I added that over. Okay. Well, I'm trying to solve for M1. I divide both sides by 7.5. That cancels. Scroll down so I can read there. M1, which is the mass of the satellite. Ladies and gentlemen, 1022.6, repeating. So with my 1022, I now need to put it into appropriate units in sig digs. So I go back up here. Okay, 2 sig digs. Gotcha. So I need to put this into 2 sig digs. So I'm going to round this thing. I go, all right, those are my 2 sig digs. I look at the 2s. That's going to round down. It has to be in scientific notation. So we're going to go 1.0 times 10 to the power of 3. I've got my 2 sig digs. Now I need units. It's mass. I started with kilograms, so that means I finish in kilograms. Excuse me. And I am now going to think, do I need direction? Nope. Mass is scalar. Ladies and gentlemen, communicate to me that that's what you want me to mark, and you're golden. So, ladies and gentlemen, that is how you do a explosion question. All right? Okay. So, ladies and gentlemen, make sure you've labeled that as an explosion, because that big starting point here of the M1 plus M2 and the V1 plus V2 and having the V1 plus V2 equals 0, that's your standard for explosion questions. Okay? So the rest of the question may have its nuances that you got to figure out, but that's the easy one. Okay, the easy one, the constant part is what I'm trying to say. And like the math is not the hardest part of physics. It's trying to get everything set up correctly so that way you have the math to do. All right, that's the really hard part of physics. in my mind. Okay, ladies and gentlemen, this is the last question we'll be looking at for this particular video. And by process of elimination, we are left with our last strategy. So I'm just going to label this one now. This is what I like to call a hit and stick. So that means you're going to have your two objects are going to collide and they're going to stick together. And then they're going to wind up going one way or the other. Okay, so this one also has some of its nuances. And as always, we are going to draw things out. So, a 1.1 times 10 to the power of 3 kilogram car is traveling east at a velocity of 25 kilometers an hour. Collides head-on, traveling west at a velocity of 15 kilometers an hour. During the collision, the two vehicles lock together. That's going to be the key word that is going to tell you that we have a hit and stick. You're going to be told that the vehicles are going to stick together. If the velocity of the locked cars is 3.3 kilometers an hour east, what is the mass of the second car? Okay. So, pop up, jumping on my page again. Okay. So, we got some work to do. Step 1. Draw your vectors, ladies and gentlemen. I know it may seem tedious, but do it, and you are going to have a much clearer understanding of what's happening. And yes, on these ones, I am going to be taking points off if you don't at least draw these things. Okay, so here is vehicle number 1. It's going to be the car traveling east. The car traveling east has a mass of 1.1 times 10 to the power of 3 kilograms. Its velocity is going to be 25 kilometers per hour. Now, for the exact same reason of what we did in question 1, I'm going to leave this in kilometers per hour. I'm not going to change it to meters per second. I'm just going to leave it. And you're going to wind up with your answer being the same in the end anyway. So, because the units are going to cancel. So I would just leave it. But as part of a physics student, it's your job to recognize when you can't tweak your units. Okay, and I showed you why in the question 1. So, well, I can easily calculate my P1. Now it's going east. I'm going to actively choose at this point to make east positive and west negative. Okay, so that means I'm going to wind up with a positive 2.75 times 10 to the 4 for my momentum of object 1 initially, and the units are going to be kilogram kilometer an hour. Okay, those are your units, and that's okay. Just for sake of space, I'm going to write the units underneath. Not per kilometer an hour, it's multiplied. Okay. So 2 is going to be the other car. That's the second car. He's traveling west. Okay. We've been asked to calculate the mass of M2, so we don't know what M2 is. Okay. And then we have our V2 as going to be 15 kilometers an hour west. I'm going to choose to make that negative 15 kilometers per hour. Okay. Well, my P2 is going to be M2 times negative 15. That's the best we can do at this point. Can't do much else here. All right. So I have calculated the before aspect as much as I can. I am now going to do my setup and calculate the after. Now, these guys are going to stick together, okay? So that means objects 1 and 2 are stuck. You can draw them like that, or you can draw them what could be easier is you can draw it something like a rectangle with a circle in it and go 1 and 2. Like it doesn't matter exactly how you draw it, as long as you draw it in such a manner that you recognize the objects are stuck together. Well, they are going east afterwards. Okay, so, well, M1 plus 2, what is that? We don't know. So it's M1 plus M2. It's really what we can do right now. Okay, we're going to leave it at that. We're just going to leave it like that for now. RV 1 plus 2 prime, well, that's going to be 3.3 kilometers per hour. And P 1 plus 2 prime, well, not a lot we can do with this one at this point other than 3.3 times M1 plus M2. That's as much as we can do right now. Can you guys foresee the algebra coming? Algebra's coming. Be prepared to bust out your algebra skills. Oh yeah. So, the same as we always do when it comes to conservation of linear momentum, we've got the sum of your initial momentum is going to equal the sum of your momentum prime. Okay, so that is what we're going to be doing. Now, we are going to have some fun stuff. We know what we've got over here, okay? At least for the most part. Let's put down what we know, okay? We know that we have 2.75 times 10 to the 4. I'm just going to leave units out for now, just make it easier on the algebra, plus P2. I'm just going to write it as P2 for now, okay? And this is going to equal our P1 plus 2 prime. Okay, that's what we got. Now we need to start expanding this a bit. Now, this is going to be algebraically your best friend. Algebra. It's awesome. Well, let's substitute what I got in here. So 2.75 times 10 to the 4. What we've got here is plus our, I'm going to write it down as we wrote it earlier. I was going to alternate it, but I'll just leave it now. M2 times negative 15. Okay, that's what we got here. That's going to equal 3.3 and M1 plus M2. Okay. Well, guys, we got an interesting scenario ahead of us. We've got two M2s. Okay, we've got an M2 here and we have an M2 here, and we're trying to solve for M2. So this is where the algebra comes in. So let's go and start dealing with what it is we can at this point. I'm just going to scroll down here so that way, because we've already have all our numbers in that we need from that info. If we need it again, we'll scroll up. So ladies and gentlemen, let's organize things a little bit neater on this side. So let's clean this up. So 2.75 times 10 to the 4. Well, the negative 15 times n2, well, we can, instead of adding that, we can subtract by 15m2. So that's cleaned that up a little bit. That's made that nicer. Now let's clean this up. I need to be able to deal with my M2s as their own individual chunk. Okay, so I'm going to FOIL that out. So 3.3 times M1 plus 3.3 M2. Okay, so I FOILed it out. All right, math is coming in. All right, so now we've got something to work with here. So, ladies and gentlemen, what I am going to do here is I'm going to add 15m2 here. Okay. Okay. I'm going to subtract 3.3 m1 here. Okay. Okay. All right. So once we get that math underway, we're going to by adding 15 adding 15 m2 over here. Let's just write that down. So times 10 to the 4, I've added that 15 m2. Okay. Plus 15 m2. Okay. So I've added that 15 m2 over here to this side. Okay. Now I need to get this M1 out of this side and over here. So I got to get these M2s on their own, right? So I can start looking at some algebra here. So I'm going to subtract this 3.3 M1. Okay. And now I am going to have my 3.3 M2 and plus my 15 M2. Okay. Whew. Deep breath. So now that we've got these guys sorted here, ladies and gentlemen, I can start cleaning up this end. I'm going to clean this end up completely. Okay, let's just deal with this end. Because we do know the value of M1. So, which is, ladies and gentlemen, which we had earlier. See, you look up. There she is, 1.1 times the power of 3. So I'm going to just put that M1 in there right now. I'm going to erase my decimal point. So 2.75 minus 3.3 times 1.1 times 10 to the power of 3. Okay, so I will just write that underneath just so we can clean that up while we're thinking about it. So, whoops, I dropped my 10 to the power of 4. I can't even really blame it on Monday because it's Friday. On the day I'm filming it, it's Friday. Okay. So I do the math, multiply that out, do the subtraction, and I'm going to wind up with 23,870. Okay. So I've cleaned up this entire end now. I am now going to come over here and clean this up. Now notice, M2 and M2, these guys are the same variables. They are being added to each other. So what do we do when we have two values, the same variables being added? Well, we can add the coefficients and combine the variable. So we're going to wind up with 3.3 plus 15 times M2. That's going to give us the same value. So we do that. Then we can clean that up. We're going to get our 18.3, ladies and gentlemen, times M2. Now we've gone from 2 M2s to 1 M2, just what we want. And now what we're going to do is we're just going to divide out that 18.3. Okay, that cancels. And once you plonk that lovely value into your calculator, you are going to wind up with 1,304.37 kilograms. Okay. So, ladies and gentlemen, what we're going to do is we now need sig digs and units. Okay. Well, back in the original question, how many sig digs do we want? 2. Scientific notation, it shall be your friend. So we look at all these other values. That's going to round down. So we want 1.3 times 10 to the power of 3. Units are kilograms. Mass is scalar. So, therefore, you do not need a direction. Indeed, I do not want a direction. Box your final answer. So then, I know what to mark. So, ladies and gentlemen, I know that last one was a tough one. But there's a very good reason that we did that one specifically in that fashion. And that's because guess what is happening and what will show up on an assignment or a test or a quiz? That type of factoring question. You're going to see at least one of those in the future. That's unsettled end. Possibly more, but guaranteed at least one. So take your time with these and pull in your algebra skills from math class and apply them to these scenarios where necessary. Sounds good, guys? Okay. Now, ladies and gentlemen, our next video, we're going to be taking the conservation of linear momentum, and we are going to be taking it and going a step further here. Okay? We're going to be graphing it, and we're going to be taking this stuff and putting it into y equals mx plus b scenarios. So what you need to do is, you see these practice problems up on the screen? You need to do them. You need to do a lot of them, and you need to be very, very comfortable with this concept, because what we're doing next is going to be graphing conservation of linear momentum, and we're going to be pulling back that y equals mx plus b. And we are going to be talking about graphing data and straightening curves on this stuff. So what I referred to in the first video. So you need to know how to do this, and you need to be comfortable with it. And then after that, we're going to be going and doing conservation of linear momentum in the 2D, which is even more complicated. So you got to know how to do this stuff. So we're building on it for the rest of said unit. Okay, guys? Cool beans. Do your practice problems. Do the assignment questions that I'll give you on Google Classroom to do. And we will see you next time. No fires, injuries, or explosions. Stay out of the way of rampaging viruses. See you all later.